Hello everyone. In this video, we will see some basics about binomial distribution and the definition of binomial distribution. Along with that, how we can find mean and variance from the moment generating function of this distribution. So first of all, let me explain why we are studying this binomial distribution. In reality, there are some cases where exactly only two possible outcomes will be there. We'll consider that as success and failure. For example, you see the first line, the binomial distribution, it is a discrete probability distribution, okay, that models the number of successes in a fixed number of independent Bernoulli trials. So Bernoulli trials is a nothing but it is a random experiment having only two possible outcomes or with two possible outcomes. Okay, so we are going to name that outcomes as success and failure, and note the word fixed number of independent trial. Fixed number, so we are going to take that number as a finite value n. Since this is a fixed number, we are calling this distribution as a discrete probability distribution. And this type of distribution is widely used in physical cases where only two type of outcomes will come. Okay. Next one, so let us see the definition of binomial distribution. So if we want to define a binomial distribution, we have to define its probability mass function, and note that the word mass will be used for discrete cases, and if it is continuous case, we'll use the word density. So a random variable x is said to follow a binomial distribution with parameter. See, for every distribution, the parameter is very important. Here, for binomial distribution, we are going to denote two parameters, that is n and p. N normally denotes the number of trials and p denotes the probability of success. Okay, so if we have n and p, the other parameter q, it can be determined based on p. So we are fixing only n and p as the parameters of binomial distribution, and this binomial distribution can be notated by b of n comma p. So x is said to follow binomial distribution b of n comma p if it has the probability mass function. That is, probability of x is equal to x should be, this is nothing but binomial coefficient ncx. In other words, we can write it as ncx p power, so this is x n minus x, and we have to remember the value of this x. X varies from 0 to n, so we have to be careful up to which value it ends. And we know the definition of binomial coefficient. ncx is nothing but, that is ncr is nothing but n factorial divided by r factorial into n minus r factorial. So in the place of r, it has been replaced with x. That's all. So this is the PMF of binomial distribution. Now we are going to define the moment generating function. We all know the general definition of moment generating function. It is nothing but the expected value of the function e power tx. So expected value of e power tx. This is what we are going to find. And one more thing, if it is a discrete distribution, so we'll be using the notation sum. Okay, and whatever is there inside your bracket of expected value, we are going to put that and we are going to multiply the probability value. And since the range of x is from x is equal to 0 to n, we are going to write our moment generating function mx of t as summation x equal to 0 to n e power tx p of x, and we know that p of x is nothing but n cx p power x q power n minus x. That is what written here. And one more thing, you recall this one binomial formula. So generally we know the form of this one. a plus b the whole power n, it can be written as nc0 a power 0, or we can write it as a power n b power 0 plus nc1 a power n minus 1 b power 1 plus etc. ncn minus 1, here it will be a, here it will be b power n minus 1 plus ncn a power 0 b power 0. So note that, so the general form we can write it as NCX. So see, the suffix values of this binomial coefficient varies from x is equal to 0 to n, and this power is nothing but, listen, n minus 1, it goes on like that. We can write this as n minus x b power x. The same is what written here. Instead of a, we are having, see, instead of a we are having p power x and e power px, so we are going to take it commonly, that is p e power t the whole power x. So we can take this one as b and this q as a, so we'll be having p e power t plus q the whole power n using binomial formula. So this is the moment generating function of binomial distribution. So mx of t is nothing but q plus p e power t the whole power n. From this one we are going to find the mean and variance value, and note that we can find the mean and variance value straight away. See, the mean value is nothing but e of x. E of x means it is summation x into p of x, and for variance we know the formula e of x minus x squared minus e of x the whole square. So for e of x square, we can write the formula summation x squared into p of x. But since we already know the moment generating function, we are going to find the mean and variance of binomial distribution using that MGF. So mean value, it can be written as first derivative of moment generating function at the point 0. So for that, first we have to find mx dash of t. So listen that we are going to differentiate our MGF with respect to t. Our MGF is nothing but q plus p e power t the whole power n. This is what written in previous slide. Okay. Now we are going to differentiate this with respect to n. So since we are having n in power, it will be n into whatever term we are having inside the bracket, we have to write it as it is. Q plus p e power t the whole power n minus 1 into, we have to differentiate the term inside. Q will be treated as constant. This p will be multiplication with the t variable. So we have to keep p as it is, and e power t, derivative of e power t is e power t. That's what written here. Now straight away let us substitute 0 for t. So e power t becomes 1 here, e power t becomes 1. Now if we multiply p into 1, we will be getting p. This is nothing but q. Also we know the property that p plus q is equal to 1. So using that one, if you use that property p plus q equal to 1, this term results in 1. So it will be n into 1 into p into 1, which is nothing but np. So our mean value of binomial distribution is np. Next one, we are going to find the variance value. So already I have given variance of x is e of x squared minus e of x the whole square. So we are going to find e of x square. E of x square is nothing but second derivative of MGF function at the point 0. So already we know what is mx dash of t. I'll write it once again. It is n p e power t into q plus p e power t the whole power n minus 1. So we can keep this np as constant, and there are two terms involving t. We have to differentiate it. So what they are doing is, np e power t. First they are keeping this term as constant and differentiating this one. So we'll be getting n minus 1 into q plus p e power t. Power will be reduced by 1, so it is n minus 2, and then into the term p e power t, that is differentiation of this bracket term. P e power t will be there, plus this n and p are constant, we are going to keep it as it is. So we'll be keeping this n, p and this bracket term as it is. Differentiation of this e power t is same. So differentiation of e power t is same, and we are keeping this term as it is. So now we can take np e power t commonly outside from both the terms. So apart from that, we'll be having n minus 1, this term and this term in first one. In second term, only this. Straight away let us substitute 0. We'll be getting p plus q here, p plus q here. So it is n minus 1 into p plus 1. So it is np minus p plus 1. If we multiply it, or we can keep it as it is. Now variance formula is e of x square minus e of x the whole square. So this is what we are getting for e of x squared. We already know the value of e of x, which is nothing but np. So if you multiply that, we'll be getting this term. And if we take np commonly outside, we'll be getting np into 1 minus p. 1 minus p can be written as q. So variance of x will be npq. Thank you.